All right, today we're going to dive into one of the most fundamental and honestly, one of the most powerful structures in all of modern mathematics, the vector space. And look, this isn't just some abstract idea for a textbook. Once you get this, it will completely change how you see problems in physics, computer science, you name it. So, let me start with a question for you. What could physical forces, polynomial equations, and quantum wave functions possibly have in common? I mean, they seem like they're from completely different worlds, right? Forces are all about pushes and pulls, equations are about drawing curves, and wave functions, well, they're the strange probabilistic heart of reality. But what if I told you they all share the exact same elegant mathematical DNA? So here is how we're going to break this down. First, we'll talk about the core idea. Then we'll get into the actual rules of the game. After that, we'll look at some really surprising examples. And finally, we'll tie it all together to see why this abstract way of thinking is so incredibly powerful. Let's get into it. The answer to that first big question isn't about the objects themselves, not the forces, not the polynomials, not the wave functions. It's about the abstract structure they all share. Mathematics often finds its real power when it stops worrying about what things are and starts focusing on what they do. Okay, so let's lay out that blueprint. What are the rules of the game? What does it actually take for a bunch of things to be called a vector space? Well, it all boils down to just two operations and 8 simple rules or axioms. So, formally, a vector space is a collection of objects we're going to call vectors and a set of scalars that come from something called a field. Now, don't let that word trip you up. A field is just a set of numbers where all the usual stuff, addition, subtraction, multiplication, division, works just like you'd expect. Think of the real numbers or the complex numbers. The whole system is then built on 2 basic moves. You can add 2 vectors together to get a new vector, and you can multiply a vector by a scalar to get a new vector. That's it. And these 8 rules, they are the absolute bedrock. They might look a little formal, but they're really just capturing ideas that feel intuitive. The first 4 are all about vector addition. They basically say that the order you add things in doesn't matter. There's a special 0 vector that doesn't change anything, and for every vector, there's an opposite one that cancels it out. The other 4 rules are for scalar multiplication, and they just make sure everything plays nicely together. Together, they create this really robust, predictable structure. And what's really cool is that from just those 8 rules, all these other essential properties just emerge. For instance, if you multiply any vector by the scalar 0, you get the 0 vector. Or if you multiply a vector by -1, you get its inverse. These aren't new rules we have to add. They're direct, logical consequences that you can prove straight from those first 8 axioms. It just shows how consistent and solid this whole framework is. Okay, so we've got the rules, now let's meet the players. And this is where the true power of this abstract thinking really starts to shine. You're about to see that a vector can be way, way more than just a little arrow with a length and a direction. So on the left, you've got the stuff we all learn in our first courses, little arrows, coordinate pairs in R3, lists of numbers. These are kind of the classic vectors. But the concept just explodes beyond that. Look at the right. The set of all continuous functions forms a vector space. So does the set of polynomials. What's wild is that a lot of these abstract spaces, like the space of functions, are actually infinite dimensional, which is the whole foundation of a field called functional analysis. But the thing that unites them all, they all follow those same 8 rules. For the geometric vectors, the arrows we draw on a plane, adding them together is just the good old parallelogram law. You stick them tail to head, and the sum is the vector that closes the triangle. It's a nice, visual, intuitive way to think about the addition operation. Now check this out, because this is brilliant. It shows how that same idea of addition works for functions. To add 2 functions, f and g, you just make a new function, f plus g, where its value at any point x is just f of x plus g of x. We're dealing with totally different kinds of objects, but the structure of the operation is identical. It follows all the same rules. So, if a collection of arrows and a collection of functions can both be a vector space, how do we even begin to compare them? How do we measure their size or their complexity? Well, that brings us to 2 absolutely crucial concepts, basis and dimension. Think of a basis as the set of atoms for a vector space. It's a group of vectors that has 2 really important properties. First, they're linearly independent, which is a fancy way of saying there's no redundancy. You can't make any of the basis vectors by combining the others. And second, they span the space,
meaning you can build any vector in the entire space just by scaling and adding up your basis vectors. It's the most efficient set of building blocks you can possibly have.
The dimension, then, is simply the number of vectors you have in your basis. And here's the kicker. A really fundamental theorem in linear algebra tells us that even though a space can have lots of different bases, every single one of them will have the exact same number of vectors. This gives us one single, unique number that perfectly captures the size of the space. So, for example, the physical space we live in, R3, has a dimension of 3. Why? Because you need exactly 3 independent vectors, like the classic I, j, and k along the x, y, and z axis, to pinpoint any location or direction in that space. And that leads to this truly profound result. Any 2 vector spaces that are built over the same field of scalars and have the same dimension are structurally identical. They're isomorphic. So what does that mean? It means a 3-dimensional space of polynomials is, from an algebraic point of view, completely indistinguishable from the 3-dimensional space of arrows we live in. They're just different costumes for the exact same underlying mathematical structure. Okay, let's zoom out for a second. Let's appreciate why this level of abstraction isn't just some neat mathematical trick, but an incredibly powerful tool across all of science and engineering. By thinking in terms of vector spaces, we create this single, unified toolkit that we can apply to all these different domains. Quantum mechanics, it's all built on Hilbert spaces, which are just a special kind of vector space. General relativity uses tangent spaces to describe spacetime, and things like computer graphics or data science are fundamentally about manipulating vectors, whether those vectors represent points in space, colors, or features in a dataset. What this does is it gives us a common language. It lets us translate ideas and tools from one field to another. An algorithm that was designed for processing images could be adapted to analyze economic data, all because both problems can be framed in the language of vector spaces. This is the power of abstraction. It reveals the hidden connections between problems. So, after this quick tour, what's the most important lesson? What's the one big idea you should walk away with from all this? This is it. The most important thing is not what the vectors are. It doesn't matter if they're arrows or functions or polynomials or matrices. What matters is that they follow those 8 rules. The real power is in the structure of how they add and scale. The identity of the objects themselves is almost an afterthought. So I'll leave you with this question to think about. Where else can you find this hidden structure? Once you start looking for collections of things that have a well-behaved addition and scalar multiplication, you'll start seeing vector spaces everywhere. And it'll give you a powerful new lens for understanding the world.